All right. There are three numbers you should memorize regarding the normal curve, and that's these. The area under the normal curve between plus and minus 1 is 68%. Between plus or minus 2, actually plus or minus 1.96, is 95%. And between plus or minus 3 is 99.7%. Right. On an exam, I will expect you to know those numbers. I will not expect you to know any other areas under the normal curve. It's a worthwhile exercise to figure out how to take areas that are tabulated like this and turn them into more complicated things, but I'm not going to go through that in class. It's something you guys can figure out on your own. Okay. The other thing that I wanted to say about this is if you're talking about a random variable that can only take integer values, like a binomial random variable, then it can make the normal approximation better to think about the bin in the probability histogram that corresponds to the range that you're talking about, rather than taking the value at the center of the bin. So let me just draw a little picture. Okay, so let's say we have a random variable, and the probability that random variable is equal to minus 3 is, let's make that minus 2, because that's a little more realistic given the way I've drawn the curve. Okay, so the area of this bin would be the probability that the random variable is equal to minus 2, right? Everybody, we're all calibrated here? Okay. What's the area under the normal curve under the point, over the point minus 2? 0. The area under a curve for any point is 0. Yes? So if I wanted to find out the chance that this random variable is equal to minus 2, finding the area under the curve between minus 2 converted to standard units and minus 2 converted to standard units is going to give me 0. Right? It doesn't help. Yes? So what I want to think about is the fact that if I have this random variable that can only take integer values, the bin that corresponds to minus 2 would go from minus 2.5 to minus 1.5. Right? It has some width. And I want to approximate the area of that bin. And so the area under the curve between minus 2.5 and minus 1.5 is going to be a better approximation to the area of that bin than simply taking the area under a point. And it's kind of in general true that you want to think about what are the possible outcomes that are contained in some range and expand things to include so that they correspond to the bins you're trying to find the area of. All right, so if we had, for instance, a binomial random variable, now remember, a binomial is like the sample sum of draws from a 0, 1 box, where you have a proportion p, a fraction p of the numbers in the box are 1, 1 minus p of the numbers in the box are 0. We draw with replacement a fixed number of times little n, right? That's got a binomial distribution. So the possible values of a binomial are from 0 on up to the number of draws, and only integer values are possible. When we draw the binomial probability histogram, we typically draw it so that the bins go from, the bins are spread around the integers by going up and down by half. Yep. So this bin goes from 1.5 to 2.5. And if we wanted to approximate the area of that bin by the area under the normal curve, what we would do is find the area of the normal curve between 1.5 and 2.5 after converting those values 1.5 and 2.5 to standard units. So let's look at the normal curve here. Okay, so the claim is that the area under this curve between 1.5 and 2.5 is about the same as the area of this rectangle between 1.5 and 2.5. So here it's a little too low, there it's a little too high. Those things almost balance, so you get about the right area if you go from a half integer to a half integer. So let's actually see how those numbers compare. So if we went from 1.5 to 2.5, then the actual binomial probability is 4.4%. The normal approximation of that is 4.3%. Okay, it does that well because we're really approximating the area of the bin. We're trying to say, okay, area under this region, not area under a point or something like that. So if we wanted to find the normal approximation to the probability that this random variable is between 2 and 5 inclusive, that is that 2 is less than or equal to x is less than or equal to 5, what region would that correspond to? We would start at 1.5, right? And we would go up to 5.5, okay? Because we want to include, if we want to include 2 at all, we want the whole bin that includes 2. If we want to include 5 at all, we want the whole bin that includes 5. Okay, and if we did that, then, I'm sorry, it was 1.5, just 5.5? Okay, so 61.2%, 61.1%. Not a bad approximation, and this is just for 10 draws from this box. All right, this box has 50% ones and 50% zeros in it, right? The hypothetical box we're drawing out of to create the binomial distribution. Is that skewed? No. If we wanted to make the distribution of the numbers in the box skewed, what will we do to P? We make it really close to 0 or really close to 1. Really close to 0 would correspond to right skewed. We'd have a bunch of zeros in the box and only a few ones. P close to 100% would be left skewed. We'd have a bunch of ones in the box and only a few zeros. If we do that, what's going to happen to the normal approximation? Is it going to get better or worse? Okay. Going to get worse. So, for instance, what's let's just look at the chance from 0.5 to all right, so here we're off by more than 1%, which is actually more than 10% of the answer. Yep, the actual probability that it's between 0 and 1, sorry, that it's equal to 1, between 0.5 and 1.5, is about 9%, but the normal approximation is giving us a bigger number. What's going to happen if we go to something like between okay. In fact, the chance that it's equal to 2, between 1.5 and 2.5, is about 0.5%, and this says that it's 10 to the minus 4th percent. Way, 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 way off in a relative manner. You know, the relative error is huge.